Yeah, almost 9:30. As always, unmute yourself and speak. Friday, I got a bunch of kits in the checkout. As always, if I can do something to make you safer, let me know. There aren't a lot of people in EER, but when you go in there, avoid them. Questions about anything? I'm going to finish up one more demo, I think. the and then we're going to go back to fundamental theory. What I did last time was the last one I did, I think, was the collector sensor. So let me review that one. Okay, so application main. Okay. Now this is Code Composer Studio with TI-RTOS. And so, you know, it's not at all like 445L, but it's probably good for you to see how professional code is made. This is the sensor sub-gigahertz. TI calls it their 15.1 protocol. Now, this is not bare bones like the HC12. This is one step up. There's a little bit of layering, but even on top of that layering, you can put your own layering, okay? So, yeah, there are a lot of files in here, and where they all are is sometimes hard to find. But luckily for us, both projects, both the 15.4 and the Bluetooth, fairly well documented with a sequence of learning modules on the TI website. So you'll see that if you go to do either of these two. Oh yeah, the board I'm talking about is the the CC1352R. And there's 3 kits, I think, which could be used for lab 1 or lab 2. And I'm going to demo lab 2 today, but I'm reviewing lab 1. Yeah, there's a lot of compile switches in here that lets you know there's different sources. Okay, so extern pointers, CC, MAC address, assert handler. Where's the interesting stuff? Okay. This is the TI method of setting up ports, as they set up a, you know, they don't actually, well, eventually they twiggle in on the IO registers, but they'd rather set up a data structure and call it. Okay, so this is setting up the what you call it, the initialization for it's not a, this is the sensor. So this is the 1351 and not the 2650. That's the other thing about professional software, is the same application will run on multiple platforms. And so you can see when it's grayed out like this, this is not going to be executed. This is the main task. Okay, this is the main task that will get scheduled. And you can see down here, it will initialize the sensor and then process the sensor. So this is one of the foreground tasks that runs in the foreground, processing the sensor. So when you're asked to figure out where stuff happens, it's in sensor process, which we looked at last time, which is in the sensor.c, which performs the reading of the sensors, et cetera, and passing the sensor process. I should have called it whatever. call it? Sensor process underline. Okay. There it is. Okay, so this is the thing that's being scheduled by the OS, which is going to collect some data and send packets out to the collector, which is going to receive it. So when you go to do lab 1 and you're going to modify something, it's in this program here that you're going to modify. Okay, so it's here, it's collecting the data, performing the message, you know, sending the message. Reading the sensors, creating an event, and then sending that message. Okay, let me show you one more thing. Let me show you here. Okay, so there are a lot of threads. Some of them, just like any RTOS, some of them are foreground, some of them are background. You can the word in TI land is task, or task function is a foreground task. Handler is a background task, okay? And so again, just like the word task in TI word is the foreground tasks that get scheduled by the scheduler, okay? And just like all operating systems, once you configure which tasks are going to be run and you schedule those tasks, you start it and then you never return. Any questions on lab 1 with CC 1352? Okay, let's do lab 2 then. With that. All right. So again, lab 2, like lab 1, is fairly well documented on the, you know, in the Simple Link Academy. There's a sequence of tasks to do, and you just get into the gift shop and make small changes. So it's, I don't, other than the fact that it uses TI-RTOS again, and let me open a couple of things. We saw last time that rather than program the radio with C code, they program the radio with the system config file, which gets burnt in, loaded in when you download the application. And so the one that the lab 1 was the TI 15.4. The lab 2 is obviously Bluetooth Low Energy. And you can see it, this particular device could handle other protocols like Thread or Z stack. Okay, so I don't believe there's any action items here to change, but when we do Bluetooth Low Energy, you will see that the settings in here can affect the power. In other words, how often does it try to connect? How often does it request connections? So I'm not going to change anything there. Let's go back to, let's close that one, let's go back here. And you can see that again, just like the other one, this whole set of projects could potentially run on more than one platform. We're not, for this particular lab, we're not using the CC1352R. Now we did in the lab last time, we put the CC1352R either on the educational booster pack or we put it on the robot and did Bluetooth. Here we're using the 1351R, okay, or 1352R, sorry. So we're using this device here, and you can see that this particular project would work for either of those two platforms. So we're going to use the 1352. Okay. Your goal in every lab, okay, is not just to make it work, but every lab is to explore the existing starter code, because we're not going to do any lab without either firmware given to us or software. but your job is to figure it out. And so once you do one of these labs, regardless of your platform, I want you to struggle to understand what it is that it's doing, okay? Now, this is Bluetooth Low Energy, and so there's a lot of things that are called handles, okay? And so let me pose the audience. Unmute yourself and tell me what a handle is. Where have you heard that word before?
Handler is a specific function that's called from an interrupt. So in the NVIC,
Okay.
usually each interrupt has its own handler and a specific pointer
No,
points to it.
not with an R. Sorry, did I misspeak? I meant handle without.
Oh, handle? Oh, I heard handle.
That was the right
My
question.
apologies.
That was the right answer for handler. I want the word handle.
Oh, yeah, usually that's a pointer to some sort of struct.
It's a pointer. So, but it's more, if you think, if you were back in 312 and I said, what is a pointer? The answer would be it's an address to a thing. And back in 312, the thing, and even in 422C, the thing was not very complicated, okay? But once we get in, you'll see a lot of handles in Bluetooth Low Energy. They are pointers to very complex data structures, okay? And sometimes they're not pointers. Like, look at this. What type is that? It's a handle. It's a connection handle, but it's not a pointer. What is it?
It's an integer, unsigned integer.
Integer. But between you and me, it's still a pointer because there's a list of connection sockets or whatever they call it, and that's the number of the number of the connection they're going to use. But it's still logically, it's not syntactically from a C standpoint a pointer, but logically it is pointing to something very complicated. So you'll see that in Bluetooth Low Energy, okay? That are, okay, so handle, struct. Obviously the word phi we'll see is the physical layer. Again, we see the TI-RTOS, TI-RTOS worm version. This is going to be a foreground task. And the, okay, cues, handles. Okay, this, let me show you this. This is kind of fun. You remember you love your 319K way back when you learned microcontrollers, and you fussed with you know, configuring the IO ports. This is the TI mantra of port initialization, and basically it is an array of pins. You see the comma. The comma is the array, and it specifies the type, and those are obviously output types for the two LEDs. Just like the TM4C and the MSP432, you can set the drive strength on the pin. Okay, and then there are the inputs, same sort of configuration. So if you're going to add more inputs and outputs, you're going to need to add more inputs and output here. What's this? Everyone know what that is? It's FE, but what is it? That's a 312 question.
Is it just the array terminator?
Yeah, so just like in 312, you learn in 319K, you could, when you have an array, you can specify a fixed size, but if you have a dynamic size, you can either pass in the size, or in this case, FE represents the sentinel, as your poly would call it. That's the sentinel. Why is it static? Okay, I want you to understand their thinking. Okay, you want to drill into their mind, and you ask the question, why is it static?
It's a private function.
It's a private function to this file. Now I don't know why it's a private function, but that's what it is. Now they're not too bad. Texas Instruments is not too bad, and or I've stolen from them. What does the syntax project 0 underline mean?
I think that's the idea of the object where
Yeah,
all
so
of
this
these
is their
functions are part of the
C++.
file.
Yeah, sure. This is their C++. This is not C++. This is C. If it were C++, that would be the class from which this method function would exist. Okay. What do you suppose this means? I like this style, by the way.
Pointer to indicate
It's a pointer.
pointer.
Yeah, and because the thing about a variable in any language, what it is obvious at the time of declaration, right? So if I gave this any sequence of letters and I gave you this much of it, you would know exactly what it is, right? It's a pointer to a GAT message event, okay? But if I just give you P message, just this part, you need to be able to extract what it is. Let me see another one. How about this is another thing that I like, that I use a lot. What is underline T?
Type.
User-defined type.
A user-defined type. Okay, so there you get that. All right. So now these are all style things. When you're grown up and you get to be boss, I want you to choose your own style. Okay, so where was I going? I was doing this wrong. So I don't want to get too much into the weeds here, but when we get to Bluetooth Low Energy, we're going to be learning about services and characteristics and whatever, and that's all embedded here in terms of how it was configured. Spin, okay. What do you suppose this is?
Just waiting.
Yeah, what does it do? What consequence does this function have?
Spins forever.
Yeah, but okay. But does it have any does it talk to the world? Does it have any, if you were drawing a data flow graph, would there be any arrow into this or out of it?
No, just
No, that's a local variable X. And there's no input parameters or output parameters. This has no effect on the external world. Why is it there?
Usually it's some
Just
sort
for
of
OS.
error catch.
Yeah, error catch. So
Oh, you think you actually called it? Maybe it could be an error catch.
maybe for OS, just to keep it running, keep the processor
If you
running.
make this the lowest priority thread, okay, and you were to debug this, what would X mean?
The number of
Your
idle
time.
Yeah, that's the
idles
that
instruction.
could be an idle. That could be an idle thread, either because the OS can't handle all threads being blocked, like we did in 445M, or it could be an actual diagnostic that would let you know how much idle time you have. So if you were debugging this and looking at X from the debugger, if X were crawling along very slowly, you're almost out of processor time. Or if X weren't changing at all, somebody's crashed. You've got some sort of deadlock. But I don't know what it is.
Isn't an 8-bit idle time pretty small?
It's a question, is it changing? I don't know what that's your job to ask the question. I don't know. I don't have the answer to the why is it there. Okay.
Okay, fair enough.
All I know is I will ask questions about everything. Okay. That's my what do you suppose this does? I bring it up because it's
Creates a task.
yeah, creates this is the initialization for TIR toss, right? This is how you launch a new thread, right? So if you want more threads, this is the syntax to create more threads. Okay, so here's the init. Again, in here, you know, there's the initialization of the pins. There's the initialization of the LED, the output pins, the input pins, the button pins, debounces the switch for good reasons. All right, so now we're getting into the Bluetooth stuff, but again, we're going to talk about all these things when we get there. But services are characteristics and all those things are happening here. Okay, log info. You can see this is debugging. In this particular case, it'll stream interesting crap out the serial port. So this is initialization of the Bluetooth project. And that is, right? Oh, we already know. What kind of thing is this? Just from the name, right? This is a method of the class project 0. What does this tell you? Right, actually, the whole thing. What does this tell you in TI RTOS land? What type of thing is this?
Well, it says it's a function for a given task, but
Well, but
in terms of what the entry point is, I'm trying to figure that out.
What does the word task mean?
The
Foreground
foreground
Yeah,
thread.
a foreground thread which runs, right? You can see the infinite loop here. And so you might imagine that that the Bluetooth, in order to process, the other one had it. The other Bluetooth example had this periodic task to process the Bluetooth events. Okay. Anybody heard the word pend before?
Yeah, semaphore.
Yeah, but which one? What's synonym for pend? Which one is that? Is that wait or signal?
I believe it's signal.
Yeah,
But I
50, you missed it. It's the other one. Yeah.
Wait, yeah. Wait, obviously.
Yeah, it's wait. Yeah, it's the wait. Yeah, post is the signal. At least I think. That's what it is in Micrium. All right, let's go on to. All right, so embedded in here are the way in which it handles the Bluetooth process. All right, so let's not. Okay, so let me go down to main. And the other main, I think the main is in this one. So it's it's not, it's Bluetooth. It's not simple. This one, if you remember the Bluetooth example we did, the other one, the one on the fitness device and the one on the robot, much simpler than this. But obviously this is way cooler. Button press. Yeah, so this, okay, so again, you'd expect this to be something that returns, okay? It handles the service associated with the value change. It's the thing that's actually going to change the LED on the board. So in here, you'll see that it does output. Now again, no memory, no bit banging. It outputs to the red LED characteristic value. Okay, so yeah, so this is good code. It's just complicated. All right, let's go to, I'm going to show you the main. I don't know where I missed it. I might have missed it. Let's do it the easy way here. Project 0, main. He said, all right, not in here. Sorry, not bound. Application. Where do you start? It's not a bad place to start at main. Okay. Where was it? Yeah, that's the other thing. Stupid TI. They hide everything from you. There will be a main in here. Include. Drivers debug. includes, no, I don't know. There will be a main. I did this. Oh, generated source now.
forget, is it in a startup? I thought it was in startup.
Could be. Thank you. There it is. Sorry. Yeah, I don't know. I prepared for this. Like, yeah, there it is. Okay. So the main here is like all the mains in thank you. TIRTOS is it initializes anything that should be initialized before the OS starts. The UART is used for printf and logging. You know, you've got your tasks and then it starts. Okay. All right, okay, enough of that talk. Let's run. Okay, build. If you remember the last one, the last Bluetooth we did used light blue or BLE scanner to interface. Now, there's not much interesting. There is a board plugged in and, you know, the interesting thing, cares, let's go. Okay, I've got to run, right? Run. Down here in the terminal is, you know, what happened. Let me clear it. Clear. Disconnect. Clear. Stop. Stop. Restart. Restart. Go. Okay. All right. Old-fashioned way. Quit. Okay. Down here in the terminal is the debugging information. So when you're trying to figure out what went wrong, having a window open is very helpful. The other example did this as well. It registered a service. You know, it said it registered the callbacks. What's a callback? Have you heard that word before?
Yeah.
What does it mean, callback?
It's a function that gets executed when an event happens.
So it's a dynamic, it's a function pointer, if you'd like, that is established dynamically. And in this case, the activity on the phone, when I push LED here, is going to generate a callback back into the user code to perform either an input or output of that function. Okay, so I registered all the callbacks for the services. You can see it's got a bunch of services, okay? Yeah, and then it sets up the advertising, and now it should be advertising. Okay, so let me quit this so you can see better. All right, so on this one, okay, so gotta do this backward. I can do, yeah, do this backward. All right, so look at, this is the phone. Okay, where's the, okay, there is an application that you can download. I think it's on both phones, both the Android and the, it's called TI Starter. Okay. And yeah, this one's a little cooler than the other one because it's actually linked. And okay, is it going? Yeah, my thing is going. And so you can see there is a project 0 is one of the choices up here. So I will click project 0. And now I have the ability to interact with the, the ability to interact with the device using Bluetooth Low Energy. And so I can do what I did with the other one and go down and look at the characteristics. Oops, I can't cancel. I can go down and look at the characteristics. Service Explorer. So if I click Service Explorer, then I'm in something that's very similar to, you know, light blue or BLE scanner, where I can peek, you know, poke and peek, set and read and whatever the individual characteristics. But the interesting one is the project 0 sensor view. And so now sensor view, if you take my word for it, if I click that button, the light on the launch pad went on. If I click that button, the other light goes on. I should. Here. Stop it here. System. Plug it in over here. Start over. All right, same deal. Okay, so now I'm going to do it this way. Sensor. Okay, so start over. Okay, back goes your starter. Crashed. All right, so stop. Stop that. Start over. Come on. Yeah. He said. Whatever. Step-by-step guide. IoT easy. He said that was going to work. All right. Here we go. I don't know. Lost it. Anyway, let's try that again. But you can push the buttons. I'm going to demo one more thing. Yeah, the advantage of hooking up the streamer is if I had the serial port open, it would have told me what I did wrong. Run. All right. Okay. Now let's try it again. All right. Back again. I don't know what I did wrong. One more interesting one is there is a. Okay, I can reach it. All right. I don't know if you can see. Okay. Push. Okay. Back over here so I can see on the screen here. All right. But there's a plot. Oh yeah, you can see it. I can see it anyway. There's a switch versus time plot on the second. I'm going to slowly dysfunctional. You're gonna have to try this. Right in the middle, there is a graph that is plotting buttons versus time. That's called a notification. So there are three things you can do with Bluetooth. You can send data from the client to the server. You can send data from the server to the client. Both of those are initiated by the server. And then there's one more called notification, which is initiated by the client. But yeah, Bluetooth will be fun. And we have a whole section on it when we get to there. Questions on that demo? Yeah. So, okay. I think I'm done with that one. Okay, so let's stay over here. All right. I do believe where we left off last time was the question. We were in architecture. And we asked the question, what is the important factors in choosing a, what are the important factors in choosing a yeah, this is where we were. If you're going to use, before we get to choosing sub-gigahertz versus Bluetooth low energy. The question is, should I choose Silicon Labs or should I choose, Nordic Semiconductor? That kind of question. And do you have any? Would you want to summarize where we were last time? What was the most important design a choice parameter that we want to think about when it's choice time? Because that's the essence of architecture, is making choices.
Documentation and support.
Okay. I'll get you number 2 on that one. Documentation. Yeah, let's use the word training. And let's put sort of responsive, because it's actually 2 different things. Having somebody answer your email that says, I'm stuck, what happened? Now, I don't know what kind of training you like, whether you like PowerPoints or videos or text or books, whatever. It's a, yeah, almost my experience with hooking these up, almost none of the documentation was ever, anything, almost none of it that actually was helpful in solving the problem was in a data sheet, by the way. Was in reference designs. Anybody want to add something to the list? Actually,
Maybe how expensive it is, what's the cost of it?
Sure, not unimportant. But if you optimize for cost, you'll never finish.
The drivers, written software.
Examples, yeah, sure.
Are you supposed to be screen sharing, Dr. Valvano?
Oh, I'm sorry. Yes, I'm sorry. Yes, I am. It looks beautiful to me. Okay. Yes, sorry. Yes, thank you. I am. What's the matter? Can't you see it? Yeah, I'm writing all this down. It's beautiful. Okay, fine. Yeah, you want to hear a funny story? Yale Pat's teaching 460N this semester. Have you heard this story? Now, you've all taken a class from, well, most of you have or will take a course from Yale Pat. Apparently his first day on Zoom did not go well, and the kids were making fun of him. So I appreciate you fixing me before the end of class. Thank you. So I don't have to, yeah, okay. So yeah, this is the last slide in the architecture PowerPoint. Okay. So reference design, drivers that work. So I separate out examples from drivers, because drivers is the code that actually performs the operation. And almost every manufacturer is going to have working drivers. In other words, programs that actually do what they say they're doing. But what a reference design is an example of how you call those drivers, okay? One that's specifically exactly like what you want to do, okay? And so, and someone said last time, prior experience. Or if you have experience in your group. I get this all the time. Kids, they go out to work and they say, well, the only processor I know is the TM4C 123, and my boss wants me to use ST Microsystems. What should I do? I said, time to learn a new processor. Do you want to, that's why I put it down on the list. What you've done in the past is kind of fun for learning, but it should not drive your design choices in the future. Anything else you want to add to this list?
Good IDE support.
Okay, sure. An IDE. Oh yeah, no, totally. Yeah,
I mean,
sure. Yeah, no. Okay, it goes really up there. Thank you, Austin.
Nordic is a
Yeah,
tragedy.
no. Let me put it. Yeah, it's so important. Now, what you mean by IDE support is the debugger, I assume.
Well, I mean, just building a project, like Nordic building a project from scratch is just not possible. I mean, it's so tied to their examples.
Yep.
And
Yep. And people ask me, why is it we teach Kyle when Code Composer Studio and these other things are way more featured. And yeah, it's new projects. Yeah, so I don't know. I mean, I think it took me a long time. It actually took me a fairly long time in Kyle to learn how to make a new project. But once I did, it wasn't that hard. It's I think if you were to look at the MSP432 examples, the projects that use the MSP432 with the Code Composer Studio that we've set up for you, these will be very easy to create a new project with. I do believe what I just showed you with Simple Link, TI-RTOS, Code Composer Studio, I think those be very difficult. Yeah, do you want to hear a funny story? You know how the first Code Composer Studio project ever made on my computer, do you know how it happened? Yeah, a past 445L student working at TI drove down from Dallas, sat in my chair, and walked me through it. I mean, that's how. Yeah, so don't hate on Nordic Semiconductor. You can love on a thing like Kyle, but this, creating a new with this platform, either with the robot RSLK or the MK2 booster pack. Those two platforms in this particular environment are actually very easy to create new projects for. And you can see from the CC1352R. So I'm going to put the debugger up there. And yeah, sure. Thank you. Anything else you want to add to the list? Thanks, Austin. That's correct.
Maybe like peripheral requirement, IO ports.
Yeah, fine. You're lawyering up on me. So most microcontrollers have the standard set of serial port, AD converter, timers, PWMs, I2C. But there may be a special need. You may need I2S, or you may need CAN. You may need Ethernet. You may need 20 timers, or 50 pins. You may have a special need that's beyond what most do, in which case, sure, you wanna, I mean, this is a necessary, if your device, this is really a necessary thing. Yeah, sure. If it doesn't have the IO ports you need, then it's obviously can't be used. Sure, good. I like it. It's sort of a dull one, but it's, they're not all identical. They're not.
I got one more.
Yeah, sure.
The lifetime of the chip,
Ooh, yeah, it's a supply chain. Sure. Yeah, the University of Texas at Austin is the single only reason the TM4C still exists. Yerbality and I made that MOOC. We've got 100,000 whatever students who've gone through there. And if it weren't for the University of Texas, they would have abandoned the TM4C 123. And so lifetime of the chip, can you get them? And how long can you get them? How long do they exist? Yeah, this is a big deal in most commercial applications, is if you can establish a supply chain. Yeah. Yeah, especially if you're a big enough customer, you can go to the chip manufacturer. Now there is a whole industry that has popped up to fill in supply chain demands for chips that the company no longer wants to produce. Yeah, there's a company here in Austin called TechMoss. And they're an IC fab, not a fab, but they're an IC design house that purposely looks for obsolete parts that exist in existing product to refill the supply chain once the manufacturers have abandoned a part. Yeah, TechMoss. All right. Okay. Yeah, so we're going to talk about sensing next. Yeah, we're not going to do machine learning or security, but these are our next. So this is chapter 3, I believe, sensing. And okay, so all right. Okay, so there's going to be 3 PowerPoints here in chapter 3. This one is a long one on sensors. Let's see, it's the 9:30. I may not finish it. Now we basically, if those of you who know me, we just wheeled into my house. You know, this is really what I've spent my career doing, is measuring crap. And so we're going to look at a couple of sensors and we'll particularly look at the sensors that are prevalent in the labs as they're deployed. Okay. Temperature, distance, acceleration, humidity, light, and sound. The goal is to understand everything, right, and ask all the questions. Okay? So, okay, so after we get past the first couple of slides, all the sensors in this chapter really have a very common theme. And that is, in order to drive down the price to improve the time for manufacturing, the world of sensors are going to follow this approach. Is what was traditionally a 445L lab, where you took the transducer, you added an analog circuit, you added an AD converter, you added signal processing. We're going to integrate that entire activity into a single integrated circuit. Okay, we're not going to do that in this class. That's some other integrated circuit class, but we're going to buy them and use them and deploy them. Okay, and so we're going to see these type of sensors. Now, before we do the real one, let's just like we did for the choice of which Bluetooth chip to use, we can do the same thing for the choice of yeah, somebody's muted. Somebody's unmuted. Somebody's muted. One of you is making noise. Not well, you know. Just right. All right. we're going to go through what do we want to think about when we choose a sensor, okay? Yeah, like Wayland says, it's got to work, okay? If your temperature is 0 to 100, it's got to work from 0 to 100. If your acceleration is plus or minus 10 G, it's got to work plus or minus 10 G, okay? The Nyquist Theorem will establish how fast the sample, but if the sensor don't pass the frequencies, it don't matter when you sample. And so it's got to be fast enough to process whatever we're doing. And then sensors are sensitive. We want them to be sensitive to what we're measuring and insensitive to everything else. And so, yeah, let me, okay, I should have found it ahead of time. Hold on, let me find it. I'm going to show you sensitivity to something that is not. Okay. Okay. Oh, I should have opened this up before time. Teaching. Okay. Where did I put it? One of these two. This is a time of flight sensor. Oh yeah, this will work. All right. All right. Look at the blue curve. This is a distance sensor. Experimentally, we have a constant distance, whatever, 120 something millimeters, okay? And there is the data that I got out of the sensor. And so a very interesting question arose is this sensor is a function of something else, not just distance. You see it? You see the blue? It's supposed to be a constant. Now, okay, it's a couple of millimeters, and as far as your robot's concerned, it may not matter. Interesting is a linear filter did not improve this. It was not, I mean, that's a 32-point averaging filter. And so the red curve is still noisy. And it turns out if you look very carefully, the frequency of this noise is is not periodic. I mean, it's periodic, but it's not stationary. Okay. The time between the periods of that blue wave are not constant. And I showed it to the chip manufacturer, and they go, yeah, that's a temperature drift. So when I first turned this chip on, the chip was cold, and it's got a temperature compensation in it. But as the chip warms up, the chip is warming up and then it recalibrates, and the chip is warming up and it recalibrates. That's what this is. So you can't use a sensor until you understand how it works. Okay, that's my and in this particular sensor, it's sensitive to not only distance, but it's also sensitive to temperature. Okay. Yeah. Here's an interesting one that was kind of I found it frustrating dealing with the integrated circuit company. And one of the things that they wanted, one of their motivations in creating these chips is to make them interchangeable. In other words, they're calibrated at the factory, if you would, and you deploy them to the field and they all work the same. But every time I got another one, it didn't work the same. And so, I basically said, well, yeah, that's fine. I love the free chips, but I have to calibrate them all. And they go, no, you don't. And I said, yes, you do. Look, this one works that way. This one works that way. So one of the parameters that they try to hit is what's called interchangeability. In other words, whatever response curve you're measuring must be a function of, if it's interchangeable, then you can plug and play, plop in another sensor. For instance, there's the OPT we just looked at. You can pick this off, plug in another one, and it operates exactly the same. But it doesn't, is my opinion. Okay. Does linear is nice. What's necessary is it has to be monotonic because the sensor response curve is inverted during the calibration/response phase, as long as it's fairly linear and monotonic. I mean, obviously it has to withstand the environment in which we're going to use it. Okay. Pressure, temperature, humidity. Yeah. Yeah, as you remember what a military device has to withstand? Yeah, 50 caliber shot, right? Remember that? Okay. So some things have to be more robust than others. Anybody want to add anything to the list?
Good data sheet.
Yeah, sure. Same thing. Reference design. Sure. Yeah, reference designs. Luckily for you, the starter code for at least for the set of sensors that exist on the examples that I've put in checkout, they all have starter code that's already runs. Yeah, so data sheets. Some of these data sheets are really long. And it's interesting, who is a data sheet written for? The data sheet may be written for the manufacturer that's producing the printed circuit board in terms of layout. And it may be written for the software engineer who's doing, I2C protocols. But yeah, sure. Anything else you want to add? That's good, Austin. Okay. Waylon's going to say cost. Fine. He gets to say cost.
I was going to say form factor.
Sure, size. Sure, absolutely. I mean, if you got especially in an IoT device that you're wearing or carrying, size and weight, sure. Okay. All right, so this is out of the textbook. They've got thermocouples and thermistors in there. This is an example of the old way, where you had a separate transducer from the analog circuit from the A to D converter. Thermocouples have the advantage that they are standards. They are interchangeable. Okay, they can be replaced. They have a large temperature range. They're fairly linear, and we'll get to this moment in a second. But they are probably characterized as an accurate transducer, and I'll define what I mean by that in a moment. And this is what I mean by standardized. A type J, the green one, the type J curve is a standard response. And because I'm so sad, I lost it, but back before when I moved in one of the moves, I lost my welder. Right here, I've lost it. I had a spot welder. And you basically, that's what the types are. There is two dissimilar metals that are welded together at the tip. And that produces the point at which you're going to measure temperature. There's typically two more junctions here because these are classically copper. Those are copper wires. So depending upon what these two metals are, metal 1 and metal 2, it produces a voltage. You know, it's a small voltage, it's in millivolts, but it is fairly standard. So these really are interchangeable. So this is something that's appropriate. And so accuracy is the difference between truth and measured. We can either take a square or an absolute value. We can either divide by the maximum and then sum it up. That's average, or 1 over n. Put 100 here. And that's accuracy in percent of full scale. So again, all three of these have the same units. So this is dimensionless. Okay, so thermocouples are fairly accurate. Thermistors, this is a 445L lab, is you take another transducer, which is a semiconductor here, where the temperature versus resistance curve is very not linear, but it is monotonic. And then you use a bridge circuit, an amplifier, and a filter, and an AD converter, and software. And so it becomes low cost. It is very sensitive, but it's not accurate. Okay? And so I already defined what accuracy is, the difference between truth and measured. What factors affect accuracy? Not just for thermistors, but in general.
Tolerances between parts,
You mean
like
like
consistency.
R1, the tolerance in R1? Or do you mean the tolerance in the, or do you mean the tolerance in RG? What do you mean?
Well, yeah, any of the resistor tolerances, what their values could be in addition to that. So any of the resistors really.
Sure. Because I'm going to you have a separate one for this transducer.
Okay.
Transducer interchangeability. Not in any particular order, by the way. I don't know. They're all affected. Some one may be bigger and more. The single biggest reason? Let's go with the biggest one first.
The heat of the chip.
Okay. Okay, so selectivity. Okay, selectivity, which means the sensitivity to other things. Okay. So if you're not trying to measure temperature, temperature will then be a disturbing factor, which will affect accuracy. But vibrations, electromagnetic fields, well, not electromagnetic fields. That's my number one. Okay. Motion, gravity, where I'm looking for noise. Noise will probably dominate your accuracy, especially if you're going real time, because we'll learn this when we get further on, but the central limit theorem will motivate us using an averaging filter. That averaging filter will slow down the measurement. Okay, so noise is probably, and not the number of bits in the AD converter, that's usually irrelevant. Okay, noise. So power supply noise here. Electromagnetic field noise. It's probably your biggest noise. It's probably your factor. But one more big one. Anybody want to guess another one? What happens if even if I were to calibrate it, what happens in a year or 2 years?
Drift.
Drift, yeah, sure, drift is a good one. Okay. So the point is, this is an IoT class. You're probably out in the edge somewhere, so you're probably going to have some sensors. You know, I don't know, maybe it's a button, which means it's pretty simple, but it may be something out there. If you're producing a product that is that's collecting information, the effectiveness of your system is going to be as effective as what you're measuring. All right. So now we're going to get away from 445L and talk about specific sensors that are available. There's one of these on each of the robots. I also have these if you have a system where you're using I²C and you want to measure distance. Okay, so it's a time of flight. It's got infrared outputs, one or more infrared outputs. It has one or more infrared inputs, and it basically measures the distance to the closest object. Okay, uses I²C, and those of you who already know what I'm going to say, yeah. So chime in. Yeah, I hate I²C with a passion. I got some pictures to show you why. Okay, so again, whenever you use something, it is your job to understand everything to the point at which you can make informed decisions. You know, the speed of light in a vacuum is about 300 kilometers per second. The speed of light in air is still about 300 kilometers per second. The solution of light in space is Maxwell's equations, and you know, there's the wave equation. Yeah, there's the wave equation, the second derivative of the electric field. So you see a tight coupling between the position x and the time t, such that when you solve it, it's a wave both in time and space. Okay, that's the point of this equation. F is the frequency. This is going to be infrared. This is going to be an infrared frequency in the terahertz range. As you know, infrared's not dangerous, at least not like X-rays and gamma rays. Wavelength is obviously related to frequency and the speed. The velocity equals the frequency times the wavelength. It goes pretty much the same speed in air as it does in a vacuum, okay, because that's the ratio of those two velocities. Well, it's a time of flight sensor. So if you were to do the math, and I don't know if this is the right math or not. Yeah, this is right. I got this right. If you're looking for something that's 50 centimeters away, 500 millimeters, and you do a time of flight, so it takes 500 millimeters there and 500 millimeters back divided by the flight, that's only 3 nanoseconds. Okay. You're not sampling that in software. You're not using any digital logic to measure something in the nanosecond range. We're going to need analog logic, okay? And so what it does in order to, now there's a bunch of these. ST Microsystems makes one too. I have it if you want it, whatever the number is. Ooh. I'll post a data sheet for it. I have the ST Microsystems module as well. It's I²C. And there's starter code for it too. But this is the TI one. There's a single emitter. Like I said, it's running IR at about 300 terahertz, which means the wavelength is pretty small. You can see, get out of the way here. Get out of the way. About 900 nanometers. That's the wavelength of IR. So in order to produce the analog circuitry to to measure things on the order of 3 nanoseconds, it will modulate. So it's still infrared. It's still 300 terahertz, but it's modulated at 100 megahertz. Now 100 megahertz is a lot closer to 3 nanoseconds, obviously. And so basically it sends light here, and then it sends dark, and then it sends light, and then it sends dark, and then it sends light. And so there is a pulse train which is emitted, reflects off the target, and then received by the sensor. And basically there's a modulation block which is outputting at 100 megahertz. The infrared LED is producing the 300 terahertz. But the modulation block is outputting at 100 megahertz. Now the correlation block is basically going to mix those two together and look at the phase response, okay? And then once that phase response is processed in analog form, we're going to get a phase signal, okay? So if you, okay, and then I lied, there was a typo. I knew there was a typo. There's a typo right there. I knew there was a typo. Okay. 10 megahertz modulation, 100 nanoseconds period. So the emitter signal is 100 nanoseconds. The response is also 100 megahertz. It doesn't phase, it doesn't frequency shift it. It just phase shifts it. So again, on the odd button, but 3 nanoseconds is at least relatively similar to 100 nanoseconds. Okay, so 10 megahertz. And in order to improve signal to noise ratio, we're going to average, there's a lot of digital signal processing in there. So we're not going to get a distance, we're not going to get a distance measurement every 100 nanoseconds. We're going to take 1,000 or so of these and get distance measurements on the order of every milliseconds, okay, in order to improve the signal to noise ratio. An interesting sidebar of this sensor, the phase is directly related to the distance, all right, the delta t, because the velocity is constant, the phase, but also the amplitude. So if they do measure the amplitude, and the amplitude is really a Boolean, if you'd like to, if you like it that way, to decide whether or not there's an object. So the robot will use the magnitude of that green line to decide whether or not there's an object there.
What if your phase is so out of phase that it goes on to the next?
Okay, so that's a great question. Okay, so we did the math over here. This math was correct. Okay, that math. Okay, 500 millimeters is 3 nanoseconds. Okay, that part I don't think I made a mistake on. Okay, and so how far would the object have to be in the next cycle? You know, ratio, right? So if 3 nanoseconds is 500 millimeters, what would be 103 nanoseconds? Right? Just
like
ratio.
30 times the.
Yeah, 30 times. Yeah, and it's so far away you couldn't see it. 50 is about 500 millimeters is about as far as this sensor can see before the magnitude gets so low it can't capture a phase. Now the data sheet says it goes out much further, but you know, when I use it, I can't go further. So it's far enough away that it would have been. So if you were, whatever, 500 times 30, right? 15, 0, 0, 0. Okay. And that's in millimeters, so that's 15 meters, right? If any object that's 15 meters away is completely unobservable. There wouldn't be enough light reflected back to capture. Does that answer your question?
Yeah. What are we sampling at?
Oh, we're going to sample at like 30 hertz. We're going to sample.
No, like what is the receiver signal sampling?
Oh, yeah,
at?
no, distance to something.
Oh,
We're measuring distance.
no, like the actual like hertz. Like you're modulating at 10 megahertz. You're sampling at what, 10 times that?
No, I'm sampling at like 10,000 times that.
Okay.
It's coming out at 30 hertz, I think, is where it's coming out.
No, I'm at the receiver. Like what?
It's the same. You're not sampling it. You can't sample at 10 megahertz. That's way you could, but it's too expensive. What you're doing is you're doing a correlation, right? If I take two signals and I have what's the function for correlation? You remember what the basic idea of correlation is? How many inputs and how many outputs? How many inputs and how many outputs in a correlation?
2 inputs, 1 output?
Yeah, sure. Yeah. And what is the essence? Okay, so you got 2 inputs, X and Y. Go to RXY. Okay. And what are the applications of correlation? There's 2. This is cross correlation. I'm doing a cross correlation between X and Y. And I'm doing it in analog space, not in digital space, by the way. What are the 2 applications of correlation? What can it tell you?
How similar are X and Y?
Yeah, shape. Are they the same shape? Okay. Two waveforms of the same shape will have a correlation of 1, right? And 2 correlations that are inverted will have a -1. 0 means they don't have the same shape. Okay. But what's the other thing you can that you can get from correlation? And that is the phase between the 2. It's basically a phase measurement. If you know they're the same shape, right? If you know the same shape, if you know X and Y are the same shape, right? What is it? I meant to be the same shape. Then RXY of T is going to have a bump right here at the phase. So you can detect. So it's a way to measure phase between 2 signals of the same shape.
Don't these use digital logic to just do a subtraction?
Not yet. Okay, no, because then you need a timer. No,
Okay.
it's all analog logic.
But
It will eventually use digital logic.
ORing them and then doing the pulse width modulator, like measuring
Yeah,
the.
but not at 100, not at 10 megahertz. Okay, the point is, each of these devices, yes, you could, Austin. Yes, you could. But But I do believe this particular one, where I went too far. Right here, because there's an analog to digital converter in this system, okay? And so if they were doing pulse width, if they were doing digital timing, they wouldn't need an ADD converter.
Okay, well, so I guess what I'm saying is like you OR the 2 signals and then you feed it through an averaging filter, and then
Yeah.
that's what you're
Yeah,
sampling ADC.
Yeah, but you're not, yes, but that's what you're, okay, so you're saying it doesn't use, okay, so there you're saying it's not using cross correlation, it's using averaging of the OR of the 2 signals, maybe.
That's the way I would do it. Just
Okay. OR. Can I say I'm not quite, I didn't build the chip. I didn't build the chip. I don't know how it works, but I do know we're still in the analog phase. Okay. That much I'm sure of. And these chips have what's called mixed signal or analog front end, where it has both analog circuits and digital circuits. And eventually it comes out as a digital signal, two digital signals, the phase as a number and the magnitude as a number. Okay. With all of that temperature curve, with that calibration, nonlinearity all undone, and with the temperature compensation all in there. Okay. Yeah. So, and what is the single most dominant factor in this thing? Is really noisy. Okay. I'm just telling you, it is noisy. They all are. There's not, you know, and because if you spend $30, I don't know what this is, $35. You know, you're not getting a $2,000 LiDAR, right? This is a device, and you can see it has five light emitting diodes. There they are on the top, emitters, and on the bottom, I think it has 2 light sensors. I don't know if I showed you the bottom part. And it's got two sensors on the bottom and 5 emitters on the top. And the multiple devices allow it to send the pulses out in a certain direction and get distance in 3 different spots. Okay. It's I2C, this MSB432 implementation. Yeah, I'll come back to this in a moment. But anyway, this plugs right into the robot. Or if you want to use it on a breadboard, it can plug into a breadboard. Like I said, it will send out data. It will send out pulses in multiple directions. It pretty much can see straight sideways to the wall. Okay, so it's almost 180-degree field of view for this sensor. Whereas the data sheet talks about a very narrow range for the field of view. This is the fundamental definition of field of view. And that is, if you consider an arc of constant distance away from the sensor, and you pick a spot. Well, let's do zone 0 here for a moment. You pick a spot, and M is the maximum magnitude along that arc. The field of view is specified to the distances where the magnitude of the signal varies from 1/2 M up to M back to 1/2 M. Okay? And then you repeat it for a bunch of arcs. Okay? To determine where is your sensor. And there will be a spot, you can see this guy, you know, he's wrote 2 meters here. That don't work 2 meters. I'm sorry, it works 1/2 meter. You know, way back at the beginning of the summer, I put in a link for a low-cost logic analyzer. It's in the Canvas announcements. This is data from that logic analyzer. This is the protocol. It's I2C. This is now 445L, so I don't particularly plan on teaching you I2C, except that if you've got an I2C sensor and you don't have a logic analyzer, you're probably a very sad person, because so much of what goes on here is much easier to debug with a logic analyzer than it is to use a scope, or just, you know, I call it debugging by brute force. You write every possible code. You write every possible code, every possible software that you can write, and see which one works. That search space is huge. Whereas if you look at the data sheet and you see what's supposed to happen, you hook up the logic analyzer, see what does happen, you can answer questions like, did it acknowledge? Okay. Did I send a start? This is this logic analyzer is giving me the start start codes and the stop codes and the address and whether or not it was acknowledged. Okay. And why in the world did it negatively acknowledge that one? That's because it was supposed to, by the way. The last code on a sensor read is negatively acknowledged. An interesting IoT question has to do with bandwidth. You know, so you got to be careful. Some of your bandwidth in your system will be limited by the sensor. In order to measure distance, it has to transmit, there's 6 bytes of data. And you can see it took 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There were 6 bytes of data. It took 12 I squared C frames. And the whole thing took 400 microseconds to actually happen. Okay. There's another thing that was kind of fun. Okay, so in this one? No. So I'll show it in another one. These are some of the codes that are in the starter code for measuring distance. Basically, you execute this periodically. Okay. You know, which gets you the answer. So this can be, it takes 400 microseconds to do this. This is the thing that takes 400 microseconds. And this is simply the phase calculation. This is the Polulu conversion between the phase and distance in millimeters. It doesn't actually work, so I had to recalibrate it with a sensitivity offset, with a sensitivity and offset. Okay, so enough of, so that's a sensor for distance. The other cool one is the IMU. There's two accelerometers in the kits. This one is a board that you can check out if you let me know you want it. This will go on the robot or on any MSP430, and it measures, it's a 9-axis IMU, inertial measurement unit, and it's part of this building automation sensor pack Mark II. And in this set of slides, it shows you the accelerometer and gyroscope, and there's a separate daughter chip that measures magnetic field. All right. Again, it uses 10K pull-ups on the board, and then we'll see why that was a mistake in a second. So again, 9-axis. The one on the fitness device is a 3-axis accelerometer, and I'll get to that in a moment. Again, your job is to know the physics of how your sensors work. An accelerometer measures acceleration. If the object is not moving, the only acceleration you're going to see is gravity. And so if the object is stationary, the accelerometer will give you tilt, you know, the 3 directions of tilt relative to the center of the earth, right? And so if you're interested in orientation to the center of the earth and the object is not moving, you can look at the 3 dimensions of acceleration, X, Y, and Z, and determine theta and gamma. Okay. Now, if you're interested in motion, you can do fun things like jerk. Jerk is the derivative of the acceleration, and you can calculate jerk to see if somebody dropped it, whether it's hit the floor or whatever. You can look at jerk on that. This is a slide out of the textbook, and basically there's a spring somewhere. Something has to move. And you're sensing the motion. This lets you know that if the device is rated from plus or minus 10 G and you drop it at 50 G, it will break. The springs will fall off. Okay, so it's basically sensor, the very small size. There is an object inside the device which moves, and that's how it's measuring acceleration.
So
yeah.
for the this accelerometer, so it said in the book that it measures a capacitance change.
Oh, there's all sorts of ways to do it. The MEMS here is how is this actually measured? Yeah, you can set this up as a capacitance. All
Do
right?
you send it? Is this part of like an LRC circuit, and you're measuring the frequency
Well,
shift?
it wouldn't be an LRC. It would be probably an RC or a C versus C. Yeah, that you're measuring. Yeah, so RC to measure time.
Mm.
Yeah, so capacitive microphone is basically an RC circuit, and when it moves, it discharges charge, and so you're picking out the current out of a capacitor. There's probably no L involved.
Mhm.
These look like those are springs. Those are mechanical springs, right? Those aren't electrical inductors.
Hate to end class, but it is.
Oh yeah,
11
in class. Yeah, okay. All right. Thank you. All right. Okay. Thank you so much. How far did I go? Oh yeah. No. Way past. No. Don't let me go. Oh, seriously, my alarm. See you Thursday. Let's go ahead and finish here for a moment. Let me just summarize for a moment. What is the most important thing I said today?
Make sure your chip has reference designs.
Okay, good. From a choice standpoint, I thank you, Keishan. Whenever you do something, look for reference designs, whether it be a chip or a integrated circuit. What's the most important thing I said about the sensor so far?
Make sure it's not noisy and it's stable.
Okay. Noise is going to be not your friend. Okay, it will be noisy. Okay, so find out the noise. The other thing that I said is make sure you understand how it works. Once you understand how it works, you can understand whether or not it's the right one for you or how to make it work the best. All right. Thank you, Keishan, for pointing it out. Yes, I will. We are officially ending class. I am going to stop the recording, invite you to come back. Yeah, pause, stop. Okay, invite you to come back.